Even if you have only a casual interest in cosmology, you cannot help but have heard that a mysterious, never observed substance called dark matter pervades our universe and exceeds the visible, tangible matter by a factor of 6. Diagrams like this are found in popular television programs and in the literature. Usually, no doubt is expressed that this so-called dark matter is a proven concept. It is not. Alternative theories of gravitation have existed for over 4 decades, and these can explain cosmological observations remarkably well. Dark matter has never been observed and probably never will. In 1933, Fritz Zwicky announced that galaxies bound together in clusters were moving significantly faster than conventional dynamics predicted. He suggested that there was a substantial amount of invisible matter holding these galaxies together. In 1970, Vera Rubin published a milestone paper in cosmology. She had measured the orbital velocities of stars as they spun around the heart of their parent galaxies. Those stars were travelling at much higher velocities than predicted by Newton or Einstein's theories of gravitation. These speeding stars should have been thrown out into deep space, but there they were, moving rapidly in stable orbits. Clearly, they were being pulled by a gravitational force larger than that calculated from knowing the combined masses of the stars, gases, and dust in the galaxy. Stars in galaxies should move like the planets around the Sun, where the speed is slower the further they are from the Sun. However, the orbital velocities of swirling stars, dust and gas in galaxies increase in speed the further they are from galactic cores, as shown by these measurements for the galaxy Messier 33. This reinforced Zwicky's prediction of huge quantities of undiscovered invisible matter increasing the pull of gravity, and so the concept of dark matter was reinforced. Nearly a century after Zwicky postulated the existence of huge quantities of invisible particles throughout galaxies, nothing has been identified that would fit the supposed role. There is no place in the highly successful standard model of particle physics for dark matter particles. Although dark matter is treated by many astronomers as though it is an indisputable reality, the fact is that many decades of searching have failed to provide any evidence for its existence. Almost any anomalous motion in stars within galaxies or galaxies within clusters can be fitted by assuming a volumetric distribution of dark matter that can be tweaked to fit the dynamical data. There are much less publicized theories that can go a long way to explain the effects attributed to dark matter. These include modified Newtonian dynamics, MOND, invented 4 decades ago by Mordecai Milgrom, and modified gravity, MOG, which was the brainchild of John Moffat 2 decades ago. Here I will introduce a suggested interpretation of MOND, linking it to the properties most likely to be important in the space-time locality where Milgrom predicts that Newtonian gravitational dynamics break down. These are the Planck length, Planck time, Planck mass, and the characteristic photon energy of the cosmic microwave background radiation. Readers are referred to my paper for details of the interaction of these quantum and cosmological parameters with MOND. The link is in the description below, as well as on this slide. Just a summary of the consequences will be described here. As many of us will have learnt at school, Newton's second law of motion states that the acceleration of a mass is proportional to the applied force. 4 decades ago, Milgrom's MOND theory proposed a revolutionary modification to this law, namely that when the acceleration of a particle drops below a certain critical value denoted by A0 as shown here, Newton's second law of dynamics changes to a square law. The value of A0 has been determined experimentally to be the value shown here, namely 1.2 times 10 raised to the power of minus 10 meters per second squared. This threshold at which the relationship between force and acceleration changes is about 1/10,000,000,000th of the strength of gravity at the Earth's surface. Typically, this threshold level is reached in the Sun's gravitational field at a distance of about 1/10th of a light year, which is far outside the solar system and well on the way to our nearest star. This is the only free parameter in MOND, so it is remarkable that MOND has for 4 decades made so many successful predictions that it still survives as a viable theory of gravity today. A simple prediction from the MOND theory is that the speed of stars, which we will call v in their orbit around the galaxy, can be expressed by this equation. So v to the 4th power is proportional to Newton's gravitational constant, the effective mass of the galaxy, and Milgrom's parameter A0. This says that the speed is therefore constant with distance as the stars are moving in larger and larger orbits, as observed. In 2021, 38 years after Milgrom's original paper, an 87-page summary of the MOND versus dark matter controversy was published. In summary, the authors wrote, "Our conclusion is that MOND is favoured by a wealth of data across a huge range of astrophysical scales, ranging from the kiloparsec scales of galactic bars to the gigaparsec scale of the local supervoid, and the Hubble tension, which is alleviated in MOND through enhanced cosmic variance. Hurrah for MOND!" A paper published in 2023 analysed the orbital velocities of many binary star systems collected by the Gaia Space Observatory. This found that MOND gave a much better fit to the data than conventional Newtonian dynamics. However, another paper, published a few months later, came to the opposite conclusion, using a different sample from the same Gaia data. The latest test of MOND came out in 2024, and this came out very much in favour of MOND. For most galaxies, far away from the central core of matter, stars, gas and dust rotate at pretty much the same speed with distance from the galactic core, as shown in this 2024 paper, even out beyond the far extremities of the visible galactic disk where the so-called dark matter is not expected to be found. This is strong evidence against the existence of dark matter, apart from the fact that not a single dark particle has ever been observed. And so the arguments are raging back and forth, and will continue to ping-pong as each team of competing cosmologists vies for supremacy. There is a lot at stake. The investment in dark matter, both in terms of a huge headcount of researchers and many expensive experiments, inflames passions. In July 2024, Sabine Hossenfelder reviewed the evidence and set her mondometer firmly in MOND's favour. Dark matter enthusiasts should remember Mark Twain's words upon reading his obituary in the press. "The report of my death was an exaggeration." Leaving behind the controversy between MOND and dark matter, I propose, in my paper referenced below in the description, to relate MOND's only free parameter A0 to fundamental properties in the universe. It is known that gravitationally bound systems such as planets in orbits around a star, stars in orbit in galaxies, and galaxies moving in clusters do not take part in the overall expansion of space-time. Because the critical MOND acceleration is always inside gravitationally bound volumes of the universe, it seems obvious to me that A0 must be a function of those physical properties of local spacetime. These are the quantum parameters Planck length, Planck time, Planck mass, and the characteristic photon energy of the all-pervading cosmic microwave background radiation. Using the method of dimensions, I have proposed the equation shown here for Milgrom's parameter A0. His experimentally determined value is 1.2 times 10 raised to the power minus 10 meters per second squared, which is within 2% of the value that I've derived here on this slide. It can be seen that I am predicting that A0 is a function of the redshift, so that A0 was larger in the early eras of high redshift galaxies. This would also predict that the velocities of stars in orbit around galactic centers has a constant value which is higher than predicted by the standard cosmological model. This in turn makes early era galaxies appear to be more massive and more highly developed than expected, as is currently being found in observations by the James Webb Space Telescope. It follows that in the regime of very low accelerations, comparable with A0, the asymptotic velocity v of stars orbiting in the outer regions of their galaxy of mass m is given by this equation, where A0 has the value measured locally, namely 1.2 times 10 raised to the power of minus 10 meters per second, which is Milgrom's measured value. My proposal that MOND includes a dependence on redshift has consequences for the expected development of young galaxies as previously described, and for the use of the Tulley-Fisher relationship for redshifts above about z equals 1. The Tulley-Fisher relationship is an empirical correlation between the asymptotic orbital velocities of stars in galaxies and the host galaxy's intrinsic brightness. This intrinsic brightness is assumed to be proportional to the galaxy mass. The line put through the data is the MOND prediction that the fourth power of star asymptotic orbital velocity is proportional to galaxy mass. This shows my proposed modification of MOND for the Tulley-Fisher relationship for spiral galaxies. The data used to produce the Tulley-Fisher plot was all for low redshift galaxies, typically less than 1. There is no inconsistency between the data points and my suggested extension to redshifts greater than 1. Supposing star velocities in a spiral galaxy are measured at 200 kilometers per second. This would give an intrinsic galaxy magnitude of minus 22. If the apparent magnitude is measured, the difference leads directly to a value for the distance of the galaxy. The Tulley-Fisher chart is extensively used to derive galaxy distances. Now, suppose that this galaxy has a redshift of 2. This would change the estimated intrinsic magnitude to minus 19.5. Thus, this galaxy would actually be exposed as a dim small object, as expected from the standard model of cosmological development. Thank you for watching this YouTube video. The full details of how I derive the equations and the consequences are described in the paper, which can be downloaded using this URL, or you can click on the link in the description below. Thank you.